Okay, so let's continue with the second. Okay, so let's continue with the second section. So I'm going to talk about. So as I mentioned at the last slide of the previous session, the focus of the previous session was about stochastic stationary runtime bandits, meaning that the distributions of the arms don't change over time. We just want to learn them, but we don't know what happens. So we want to learn them, they won't change, and that's why we can learn. Now in the second section, I'm going to move to the older side of the field, which doesn't assume any of this stationary dialogue. Okay? So when you have a dynamic environment, you aim to try to interact with it, then what typically happens is that you need to know, either you aim to know when the change happened, so you use change detection, or you use other type of statistical tools, but they only work when the changes are very slow. Okay? So when changes are very hectic, or think about a more popular situation nowadays, when you are playing with you are interacting with an opponent, learning opponent. Right? Think about like AlphaGo 0, or think about like classical, standard everyday life situations. You're dealing with a human, another human. They're not going to give you the luxury to stay in one place, letting you learn, and then move to the next place. No? They're constantly changing as well. Both of you are trying to learn from each other. Okay? So the environment is going to be very, very hectic. So how to deal with this situation? Let me give you an example, as I just said earlier. So classical machine learning or reinforcement learning, even in the case of dynamic environments, they always assume that there's a nature out there. It's not a real opponent. There's a nature, it doesn't care about you. That's quite obvious. Okay? Because it doesn't care about you, it changes whenever it wants. And the change is typically slow, typically smooth, typically continuous manner. But if nature is adversarial, in this case we don't call it nature anymore, because it knows you very well, so it wants to learn, it wants to fool you, it wants to push you down. Because of this, it wants to learn what your strategy you are using. So it changes very hectically. Then in that case, you are in trouble. Okay? Example of this is a classical game theoretic problem. It's called the iterated prisoner's dilemma. Have you heard about this? So what? Okay, I'm curious. So I'm asking you. So what's the Vietnamese name for this one? Someday tù nhân. Ah, okay. Good.
Someday.
Okay, so then you might know it very well then. So just let me recap quickly. So it means that you have two prisoners, right? So you commit the same crime together, you commit the crime together, but both of you are in prison now, but each of you in a separate room, and then police comes and then interrogate you and say, if you confess, then you can get away. And we'll put your partner into jail for 10 years. Same here, it's a symmetric game. If you deny, both of them deny, then actually police not going to be able to find anything. Right? So they will put them into jail, but not for 10 years, for 1 year only, for minor crime. But if both of them confess, actually this is where interesting happens, then actually it finds out that both of them can be put into jail for a longer time. So they're 5 years each. Okay? So the classical one-shot non-repeated game theory version of this game says that the Nash equilibrium, meaning that the most dominant strategy, everybody, if they think strategy thing, everybody will choose is to confess, right? So that's the best thing they can do. And then you can do all the kind of mixed strategies, blah blah here. Doesn't really matter, but this is a one-shot game. It means that there's no collaboration, no cooperation between the criminals. But if the problem is the iterative game one, then actually they can come up with some, high-level meta strategy. And one of them is called difficult. It means that if they commit a crime over time, not just once, but like several crimes together, then they can agree in advance. They can say that we're gonna cooperate, we're gonna deny all the time. But if one time you decide to fool me, to confess, I will learn this because I stayed in jail for 10 years. So I will learn this. Next round, I will fool you as well. So it's kind of a threat, okay? That's kind of threat. Well, this is fine in game theory, but we are not game theorists. We're not pure game theorists. So we are much more interested in situations where things change all the time. And situations where actually we don't know our opponent either. Because in classical game theory, we assume that we know everything. Okay? We know the actions, we know the rewards, we know what the opponent is going to behave. That's why we can threaten them, say, look, if you fool me, I will fool you after that. But if you don't have any information, you cannot do this. But how can we still learn something clever there? That's going to be the focus of this session. Okay? The second motivation, am I using the pointer? It's not, yeah, okay. So the second motivation, for the second motivation, let's go back to the classical nature situation. Yeah? So now we assume that the nature doesn't want to fool us, but it changes over time. But the change, I already said, you can detect by using change detections or the tools for statistical learning, but they are not that very accurate if the changes are very fast. So we also want to deal with this situation as well. So when the change happens almost every round, how can we learn something from the previous round if the next round is completely different? Transfer learning is not going to work. How can we still do some kind of like exploitation here? Yeah? Good. So this is a very simplistic, very simple slide, and I would say stupid as well. It just wants to demonstrate that we cannot use the classical stochastic method to learn here. Okay? We need to come up with some new algorithms. And the reason, sorry, can I just see, am I using the right slides? Because remember that it's different stuff here, so also. Okay. Seems like I was editing a different file yesterday night. Okay, let's go with this one. So why it doesn't work? Because suppose you are using UCB to learn, right? You are using which action would be the best in the iterated business dilemma. Suppose that the opponent in the first 100 rounds, it cooperates with you. It is nice with you. Okay? And then after that, it will defect. It will try to fool you for the next 100 rounds, for the next 200 rounds, and then it cooperate again for the 300 rounds, and so on and so forth. Okay? So you start learning, you do CV, and you learn that, oh, he's cooperating, so I should start cooperating as well.